Welcome to the Lightcurve of the week from the Hoist Citizen Science Project. Since this is the 100th edition of our Lightcurve of the week, I thought I will make a little video compared to the usual posts on the social media or the website. I would like to simply use this occasion to thank all the participants for the data they sent to us, their participation in the project, and also to show you some new things we have been doing over the last year or two with some data that is actually not part of Hoist itself, but came about because of this project. So first of all, I'd like to simply show you where all our observatories are. So we have our nice Google map where we have marked all the observatories. So you can see basically every blue circle is an amateur observatory that has participated data to the project. In yellow, these are university observatories, and in red, professional observatories, also from whom we have obtained data. So you can see there's a lot of observatories in Europe, particularly UK and Spain. So we're trying to expand this across the rest of Europe, but we also have participants in the United States, which is quite nice. So you get data points roughly half a day apart from the majority that we can gather in Europe, and you also have now two observatories that take part, which are in Chile and the southern sky. So these are very helpful to observe the winter targets in particular for a longer amount of time, because the winter targets are basically 3 months or 2 months earlier visible from the southern hemisphere than they are from the north. So this is our distribution. So we're basically only lacking participants in Asia. So we'll see how we can close this longitude gap. But in total, we have now 76 individual amateur observatories who have participated data. And here we have a nice graph which shows over time how many images we have. So it's the blue line is basically over time in years on the top measured, and the number of pictures. And you can see we are currently just shy of about 35,000 images as of today. And you can see over the last 2 years in particular, the rate at which the images have come in has extremely increased. So Hoist officially started by the end of 2014. We already have some pictures which people submitted, which have been taken before we even started. But if you look, half the images that we have actually been taken in the last less than 2 years, while the project is now about 6 years old. And we already have a backlog of about 1,000 additional images that are already submitted, which have been taken over the last couple of months. And I know of a few, several hundred, which haven't even been submitted yet. So the project is basically ever increasing its amount of data that we gather. So in total, we've now made about 150 million brightness measurements of stars in all the images that we have. The green points or the green lines on the top here, these indicate times when we have published a scientific paper using some of the Hoist data. So you can see this is steadily going on. So we're analyzing data and publish. And we got a couple of further papers in preparation, and at least one master's and a PhD student actually working on further data analysis for future papers. The blue lines at the bottom, they indicate times where I've given talks and presentations about the project. So these are now almost 50 that we've done starting in 2018 to different amateur societies across the UK. And it was at one of those meetings early on, somewhere around, I think, October 2018, where I went to the Stevenage Astronomical Society, and a very impressive gentleman approached me after the talk about a data set that he had taken and if it was useful for HOIS. And it turned out that what he'd done was basically image large regions of the Cygnus constellation, in particular about a 3 by 3 degree field here in the middle, just north of the North American Nebula, which sits here, over 6 years. Every night, it's been clear he took basically 30-second exposures once every minute. And he has basically built up about 65,000 images of that region with the same instrumentation over 6 years, with a cadence of 1 minute whenever it was clear. And he simply asked us if he wanted to include that into the HOIS project. Now, one of the HOIS targets is the Pelican Nebula, which is this little reflection nebula down here, which is part of the North America complex. And that field was outside. And also the amount of data that the gentleman had was at the time when he asked us about 40 times as much measurements of brightnesses than we had in HOIS at that time. And it's still about 15 times bigger compared to HOIS nowadays. So what we decided was that we analyzed this data set separately. And that gentleman with the name Stan Waterman, he originally actually set out to find exoplanet transits in his data. And he has, since he started the observations, analyzed manually a lot of the data himself. He's found now 193 variable stars, categorized them, and so forth. So what we wanted to do is basically see, can we identify and characterize all the variable stars in a more automated way, and see, can we actually find any exoplanet transits. And so basically over the last year, we've spent a lot of time analyzing and in particular calibrating the data set. So the actual analysis is to follow. And the stars in those images, they range from about 6.5 magnitudes to about 13.5 magnitudes. And this is an example of a known eclipsing binary in that sample with a period of about 10.5 hours. And in phase, if you take the data as it is after flat fielding and you just measure the magnitudes of that star. And what you see, if you do this, there's a huge amount of scatter in the data, but the data points scatter by about 17%, and you can't really see anything that looks like an eclipsing binary. So the first thing we do is we do a basic calibration where we basically offset the magnitudes from all the stars in each image compared to a reference frame, and that improves things already quite dramatically. And you can now see there's a nice systematic behavior. You get a primary minimum, you get a secondary minimum, and the two maxima here in between. And the scatter of the data points from that kind of mean here, which represents the actual light curve, has gone down dramatically to about 4%. And once we've done that, then we saw there's still a lot of outliers, a lot of points which do not follow the light curve. And they're caused by certain issues. Sometimes there's been clouds which change the color of the star and hence the brightness measurements. There have been issues with some of the flat fields. So we spent, or master students spent a lot of time over the last year to improve on that. And once you do these corrections, you can see that most of these outlying data points really go away. And the scatter now has gone down by another 10%. So the data points now scatter by about 3.7% from the actual light curve. And you have to remember, this is the brightness of this star is close to the limit of the detection in that survey. So most of the other stars are brighter than this one and have a smaller scatter. So this is one of the worst examples that you can find in terms of noise in the data. And as a final step, what we can do is we can basically use a nearby bright comparison star to do a little bit more corrections. And then you can see it looks a tiny bit better. The noise has gone down by a further bit. So we are now down to about 3.5% of the scatter of the data points from the mean light curve that you can establish once you know the period. And this is already quite impressive. You get a nice light curve. But one thing we can do is we can basically smooth this mean light curve here by 1% in phase space. And then we can overplot in red the actual error of that mean light curve. So not the scatter of the data points, but the error of the mean. So how uncertain is the mean light curve at every point? And it turns out this is that red range here, which basically just looks like a line because it is so small. We have so many data points, about 60,000 images, that the uncertainty of the actual mean light curve at every point is of the order of 0.1%. So the individual data points, as I said, they're scattered by almost 4%, but the mean light curve is accurate to within 0.1%. And what you then can do is you can actually zoom in so that you see the two maxima here of the light curves. And what you will find is that the first maximum is actually higher by 1.5% than the second maximum. And this is called the O'Connell effect. There's a lot of possible explanations for that, why the maxima in an eclipsing binary are different. It could be spots on the surface on one of the sides of these eclipsing stars, or both of them, which makes the first maximum brighter than the second one, or it could be the other way around. And we can detect this 1.5% difference in the brightness by 15 sigma. So the error is 15 times smaller than the actual difference in the maxima between the two peaks here. So this is quite impressive, and it also now tells us that if you're looking to find exoplanet transits in our data, a typical Jupiter-sized planet around a solar-type star will make a dip in the light curve of 1%. And with that data, even for the fainter stars in the data set, we can detect this at 10 sigma. So it's a very high signal to noise that we are able to achieve with that data set after spending a year on calibrating it. So we also run some numbers and we have basically a 90% probability at least that we are able to find an exoplanet transit in the data. So a master student is currently starting to look at finding those exoplanet transits if there are indeed any in the data set. And once we have found something, we will let everybody know. I have a few more examples of light curves because it's the light curve of the week. So I pulled out some more of those light curves from the data set. This is a nice eclipsing binary of about 3-day and 18 hours period. It looks nice and symmetric. So basically both minima are roughly the same depth. So the stars are basically roughly the same size. From the distance in Gaia, we can estimate that both of these stars are roughly late spectral type B, so reasonably massive. You can see the maxima are still rounded, so the stars are not absolutely spherical. They're slightly elongated because of how close they are to each other. And if you actually zoom into the eclipses, this is the primary eclipse, which happens at phase 1. The secondary eclipse for circular orbit should be at 0.5. and you can clearly see it's not. It's shifted by 1.5% in phase space to about 0.485, which means that this is not a circular binary. It has an eccentricity of a minimum of 0.075. So this is a slightly eccentric binary with two reasonably massive stars. And we can we'll try to model these kind of binaries to really characterize what actually is going on. A second example of an eclipsing binary is this one. Again, a period of almost 5 days. And this one is different in the sense that it has a very, very shallow secondary eclipse. It's only 6% deep. The primary eclipse is almost 1 magnitude deep. So here we have clearly two stars which have very different brightnesses or sizes, which cause these different depth between the primary and the secondary eclipse. This is another example of a very short period eclipsing binary, just under 1 day period. And what you can see is both the primary and the secondary eclipse are almost identical. So these are basically almost identical stars that orbit each other. It's absolutely circular. So the secondary eclipse is at a phase of 0.5. And the difference between the primary and secondary minimum is only 0.3% or 0.03 magnitudes. So both stars are almost identical in size. Then you get these kind of binaries with a period of less than half a day. These are detached or binary stars who actually touch each other on the surface. So you get kind of just round maxima. There's no proper maximum that is flat, and you get the two minima here slightly different. You get these very odd shaped light curves. So these are basically contact binaries. And as a last example, what you also find in that field are a delta Cepheid star. So this is a 5-day period delta Cepheid star, and you can nicely see the shape of the light curve. And you can, from the period, you can estimate basically the distance or the absolute magnitude for these objects. So basically what you're going to do over the next couple of years is really try to identify all these variable stars in that field. So there's 20,000 stars that we can look at with 1.3 billion brightness measurements amongst them. So there's quite a bit of work to do. We're trying to characterize all the eclipsing binaries and really go and see, can we detect any exoplanet transits amongst these stars. So thank you very much for listening. And I hope you enjoyed our little video for the Lightcurve of the Week, edition 100.